Okay, good morning. As Professor Ada mentioned last time, today we're going to be talking about a little bit of basic number theory and arithmetic. But of course, this is a computer science class. We're going to try to take a computer science or computationalist perspective on a lot of the arithmetic aspects of number theory that we see. Okay, so we'll be talking about algorithms and numbers. So let's say B is a number. And as always with the arithmetic algorithms, you should really think of B as being a really big number. Okay? So like this, for example. That's like a perfectly nice number to work with in number theory type algorithms. It's a very big number. Actually, unfortunately, I have to go to smaller numbers because this number is, if I use this as my running example, I'll have no space left in the slides. So I'll take this number, which is actually, well, in some ways it's big, in some ways it's not that big. So this number is about 76 digits long. I looked up what this is, so I guess it's 5.7 quator vigintillion. So on one hand, it's a very big number. Okay, that's something like the number of atoms in the universe. Or it's also roughly up to some factors of 10, like the age of universe in Planck time units. Planck time is like the least amount of time. Apparently, time is actually discrete. So it's a very big number. The actual magnitude of this is bigger than any physical thing you can imagine. But of course, we don't store these numbers in unary in our computers. We store them in binary. And just to make this very clear, normally we think of how long does it take to write down a number in bits? It's like log base 2 of the number of bits. Just so it's kind of very clear in this lecture, I'm going to write this as length of b rather than log of b, but it's the same thing. It's the number of bits that you need to write down the number b. So actually, if you look at our number b, which was 5.7 quator vigintillion, its length is about 251 bits, or it's about 32 bytes. So in other words, it's actually tiny, right? It's like 32 bytes long. There's no trouble with storing that in your computer. And in fact, for, let's say, cryptography purposes, which is part of the reason I'm discussing this topic, you'll see some more about cryptography next time, this particular b with 251 bits is actually a very small number. So for example, when you use SSH, or RSA, you get some key, which is a number, and usually it's supposed to be like 2,000 bits long, which is about 10 times longer. So really, the numbers that we're typically dealing with in algorithms, especially relating to cryptography, are these ones like maybe on the very first one I showed that spanned like many, many lines. But for simplicity, we'll only work in our little examples with these ones that are about in the quator vigintillions. Okay, so I want to talk a little bit about arithmetic algorithms on big numbers. We've seen this several times before, actually, but I'm going to show you more examples today, so it won't hurt to review a little bit the earlier ones. And what you should remember is, despite what you're used to when working with very small numbers or typical numbers, arithmetic is not free. If you take some number with 500 digits in it, and you square it, it's going to take some time that's proportional to 500 somehow. And of course, our numbers are written in binary, so we're always storing them with bits, although my examples will show digits because it's a little bit more natural. And actually, because of this, you should really actually think of numerical algorithms on really big numbers as string algorithms. You should almost forget that the symbols correspond to actual numbers. It's just going to be some algorithm that manipulates the digits of the numbers as strings. Okay, and if you're kind of unused to this scenario and you kind of forget that it actually takes an algorithm to add two numbers, or it actually takes an algorithm to multiply two numbers, and I ask you how might you do these sorts of things, you should really, a good way to think about it is to decide how would I do this myself personally by hand, like if I was staring at a 20-digit number and I just had a pencil in my hand. Okay, and because ultimately that's what you do as well. You if you're adding two really large numbers, you manipulate these two long strings, run a little algorithm on them, and get the answer. All right, let's start with the easiest problem, which is addition. This is just to remind you of the situation, really. So, these are very small numbers, as I said, but okay, here's a typical looking addition problem. And again, think of these as just really long strings that might actually be 1,000 characters long or 10,000 characters long. So how do you take A and B and add them and get C? Well, you can just do the algorithm that you all learn as kids. I don't exactly describe it here, but you start from the back, and you have basically a little lookup table. 4 and 1 turns into 5. 0 and 0 turns into 0. 1 and 1 turns into 2. And there's a little extra twist with the carrying, but basically you process the characters right to left, do a little lookup table for each pair of numbers, and you get the answer. And it's easy to check that this algorithm, the grade school algorithm, is linear time in the length of the strings or numbers. In other words, if, let's say, the two input numbers have length, number of digits or bits, whatever, at most n, then the running time to produce the answer is order n. OK, let's go to the next most interesting one, which we've also talked about a lot. We had quite a substantial part of a lecture about it, multiplication. So again, as we saw when we first looked at it, there's the grade school algorithm that you learn when you're a kid. And it's also, you could think of it as just some algorithm that manipulates strings. You build this kind of table or array that looks like this. You kind of process the digits in pairs. Again, there's like a little lookup table where you know that like 6 times 1 is 6 and so forth. OK, and then you add them up. I didn't show all the details, but finally you get the answer C like this. And how long does this algorithm take? Well, actually, you can do a slightly more careful analysis if one of the numbers is a lot bigger than the other number. We're not really going to worry about this, but I'll show you anyway. Basically, the number of rows, assuming the longer number is on top, the number of rows is the same as the number of digits in the shorter number. And then that's kind of like the height of this parallelogram. And the length is something like the length of the answer. And let's just remind ourselves what the length of the answer is. We certainly have to write down the answer. So the length of C, it's log of C, which is A times B. By the properties of logs, it's log of A plus log of B, which is also the length of A plus the length of B. OK, so the answer, the number of digits in the answer is more or less the sum of the lengths, the sum of the number of digits in the problem. So if A is the longer one, that's at most twice the length of A. So basically, the number of entries in this big old table is like length of B times length of maybe 2 times the length of A. And it's not that literally the number of steps is the number of entries in this big array, but it's more or less like that. So it's not hard to check that the running time is proportional to the length of the longer number times the length of the shorter number. OK, and if you just want to be a bit more simple about it and say, let's say the two lengths of the numbers are at most n bits or digits, then this is at most n, this is at most n, so it's a quadratic time algorithm. And in the rest of this lecture, I'm not going to get too overly excited about running times. I'll mention a few things. So we'll stay at a high level and say this is polynomial time, so it's fine. But I do want to remind you that, as we talked about, significantly faster algorithms exist, and they're definitely used in practice. I mean, if you go into your favorite mathematics program, for me it's this one Maple, but other people like Mathematica. If you just have a web browser, you can use Wolfram Alpha, although it doesn't allow you very long inputs. But anyway, if you use any of these and give them two 10,000-digit numbers to multiply, they won't do this. So that'd be like 100 million steps. They'll use the faster algorithms that run in time roughly n log n. It's a little bit slower, but basically n log n. OK, so that's some reminders of things we've seen before. We'll move on to some things that we've talked about a little bit more indirectly and look at them more carefully. So we'll start with the opposite of multiplication, I think, which is division. OK, so let's say you have these two numbers and you want to divide A by B. Well, if you're doing it by, let's go back to elementary school. If you're doing it by the method you learned when you were a kid, you actually set it up like this. Actually, I recently learned when I was in another country that in many other countries, they do not draw this picture. They draw it like, it's still basically the same algorithm, but they have like a different layout where the smaller numbers on the right, or there's columns and stuff. So anyway, if you haven't been in America that long, you may not know this way of drawing it. But it's the same algorithm that you probably know. And what it actually produces is two outputs. it produces this thing at top, which is basically the quotient, a over b, except rounded down, because we're not going to get into decimals. And it produces this number, r, the remainder, the part that's left over, which is, of course, always smaller than b. So really, this algorithm kind of computes two things. It takes a and b, and it writes a as a quotient times b plus a remainder. So that's nice. And the quotient is like the floor of a over b, and the remainder is a mod b. Okay? In this class, we'll only be talking about integers, so we'll never get into rational numbers or decimals or anything. Okay, and I won't go through the details, but you could do this by hand or just check how many steps are taken by the grade school algorithm. It's, again, basically proportional to the size of this big old array you write down. And in fact, you can also check that it's proportional to length of the shorter number times length of the longer number. So if you want to be simple about it, it's also n squared. Actually, sophisticated division algorithms exist, and you can actually get the running time down to the same running time as multiplication, but that's quite tricky. Okay. Now let's move on to the other, if you think about it in a different way, the other opposite of multiplication, which is factorization. Okay, we can take like a bunch of numbers, multiply them together. What about the reverse? I give you a number, and I want you to break it into the prime factors. So let's say I give you this number, and I'm like, what's the prime factorization of it? In fact, let's just say we want to find one non-trivial number that divides into it. If you can do that, then you can repeat the algorithm. So you can do this for b equals 2, 3, 4, 5, etc. Test if b divides into a. If a mod b is 0, that's fine. We just saw on the last slide you can do this line in polynomial time. But it's a loop. Of course, you may know, we've kind of mentioned it before, that really you're going to have a bad time if you do it this way. Because in particular, for this number, the answer is this. Actually, you might think about, how did I come up with this? But I'll explain it to you shortly. But yeah, the answer is this. So the smaller one of these is this one. I think it's like 36 digits long or something. So this loop will keep going until b gets up to that number. But remember, this number is like the age of the universe. It's bigger than the age of the universe in Planck time. So in fact, you will never get up to that number. You'll not even get even close to this number. So this algorithm is just not going to work for you. And in particular, if you want to think about it not with these vivid concrete numbers, but theoretically, you probably know that you can stop this check once b gets up to root a, because if a number has a has some non-trivial factor, it has to be at most the square root of a. But square root of a is like square root of 2 to the length of a, which is like 2 to the half the length of a. So if the length of a is n, then this is like 2 to the n over 2, which is an exponential time algorithm. So actually, this is not the fastest known algorithm. There are very smart algorithms that do something more sophisticated than this, significantly more sophisticated, but they're all still exponential time. The fastest one runs in time, conjecturally it runs in time like 2 to the square, no, so the 2 to the cube root of the number of digits. And as we'll see later, much of cryptography, like when you do SSH or whatever, relies on the assumption that there is no efficient algorithm for this problem of factoring. So we'll see more about that next class. OK, well, that's a bummer. That's something that we would like to do. It's a nice arithmetic problem, but we don't know any efficient algorithm for it. Let's take a look at the closely related problem of testing if a number is prime. So it looks like, if you can't even factorize a number into primes, how are you going to do this? But let me tell you something. Let's say you take this number and you put it into your favorite Maple or Mathematica or whatever. This one I think is probably small enough that the browser version of Wolfram Alpha will let you input it, and you tell it to factor. Say factorize this number. This is the number from the previous slide that had these two gigantic factors. It'll just, you'll get the spinning thing. It'll just go forever. So you just have to manually stop it. It's too big. But if you say, OK, just tell me if it's prime, it'll like return in like 0.0 seconds, and it'll correctly tell you, no, it's not prime. So how did it do that? How did it know that it wasn't prime without like finding these two prime factors? It's kind of amazing, actually. And conversely, if you give it primes, it'll correctly say yes. So here's an amazing fact. There's a polynomial time algorithm for testing primality. I think we've mentioned this before. This is actually first found not too long ago in 2002. I was in grad school at the time, and I like vividly remember like hearing about it when I was in my office. This is Agrawal, Neeraj Kyle, Nitin Saxena with the nice mustache. And they were undergrads at the time, which is pretty cool. Although they don't use that algorithm when you type it into Maple, like is this number prime? They don't run that algorithm because it's too slow. The best known version of this primality testing algorithm invented by these three people is something like a 6th power time in the number of digits. Okay, so I mean, if you run it on like a number that's like 2,000 bits long, I don't know what 1,000 to the power of 6 is, but it's a very large number. So it's polynomial time, and it's not actually, in practice, really feasible unless you have like very small numbers. So what do they do? Well, they use a different algorithm called the Miller-Rabin algorithm, which is from 40 years ago. It's Miller and Rabin. He's a CMU professor here, so give him a high five if you see him. Its running time is basically n squared. OK, and that's what people use. Now you might say, what's the catch? Why didn't you tell me about this algorithm before? Well, there is a small catch, which is that it's a randomized algorithm. Just like we talked about last time, it's a Monte Carlo algorithm. And it makes an error with some tiny probability. But as before, you can make that probability e to the minus 100 or 2 to the minus 100 by adding a little bit to the running time. And for all practical purposes, 2 to the minus 100 is like 0. I mean, again, it's like the reciprocal of the number of elementary particles in the universe or whatever, so it's never going to happen. OK. So that's the story, the brief story of how to check if a number is prime. Now, also in the next lecture, when we start doing cryptography, you'll see that these like secret keys and things that you use for cryptographic purposes are usually like the products of primes, like very big prime numbers, the product of maybe two big prime numbers. So if you want to make a secret key, you need a really big prime number. And it should also usually be a random number, but let's just not even worry about that. Let's just say I give you some big number n, like 1,000, and I ask an algorithm, please give me a prime number that's 1,000 bits long. So if we have a candidate number in mind, we can efficiently check if it is a prime number. But maybe you'll check a number and it wasn't prime, and then you check another number and it wasn't prime. This looks like a very silly algorithm to try it. Just pick a random number, test if it's prime, and repeat. But it does work. And it does work efficiently. And actually, in order to understand how efficiently this works, you need to know this thing called the prime number theorem, which is a famous theorem in mathematics. Actually, you don't need the fully strong version of it, which is difficult, but it's enough to know a weak version of it. And it says that among all the n-bit numbers, about 1 over n of them are prime. And that means that when you do this loop, on average, it's going to take you about n tries before you find a prime number. It's like a geometric random variable. It's like 1 over this would be the expected number of trials. OK, and so therefore, you only take about n trials. This is about n squared times. So you can do the whole algorithm and generate a prime in polynomial time. And this is amazingly, basically the only known algorithm. We don't know anything basically smarter than doing this. And in fact, this is an extremely interesting example of a problem where we know an efficient randomized algorithm, but we don't know any efficient deterministic algorithm. So this is kind of an amazing problem, the problem of generating a prime number of a given length. We know algorithms that we think are run in polynomial time and are deterministic, but we cannot prove it. The only thing we can prove is that this randomized algorithm works. This, by the way, well, OK, never mind. OK, let's mention primality testing one more time. By the end of this class, actually, you'll be able to prove a simple theorem that is called Wilson's theorem. This is not, you don't have to know this theorem. I'm just using it to make a point. It gives a characterization of primality. B is prime if b minus 1 factorial plus 1 is divisible by b. So now if you see this, if you happen to know this theorem, it's not too hard to prove. You might say, why don't I just use this as a primality test? I mean, I've given a number b. I can just compute b minus 1 factorial, add 1, divide by b, check if, or take mod b, check if that's 0. And this theorem tells me that correctly tells me if it's a prime or not. What's the problem with this idea? Yeah, I guess as you all know, you cannot compute b factorial or b minus 1 factorial in polynomial time. Why not? Yeah, I mean, in fact, you can't even compute 2 to the b in polynomial time, which is simpler. At first, you might just be like, just left shift that thing by b, or just left shift the bit 1 by b many steps. But if b is 5.7 quater vigintillion, and you try to write down a number that's like 1 followed by that many zeros, that's more like particles than there are in the universe. So you can never physically write that down. So you cannot compute b minus 1 factorial or 2 to the b in polynomial time just because it takes you exponential time just to write down what the answer is. I mean, it has like an insane number of digits in the answer. Now that's a bit of a shame. And let me think about this one for a second, just even 2 to the b. What's interesting is that although you cannot compute 2 to the b in polynomial time, you can compute, if you're only worried about what its value is mod some other number, c, you can compute this in polynomial time. Of course, you can't just first compute 2 to the b and then take it mod c, because the first part, computing 2 to the b, is impossible. I mean, it takes up exponential amount of space. But you can do it nonetheless. And in fact, in general, it doesn't have to be 2 down here. If you have 3 numbers, a, b, and c, and they're all n bits or digits long, you can compute a to the b mod c in polynomial time. And this is a very important algorithm and subroutine for other problems. OK, so I mean, think of a, b, and c here as these numbers that have like 100 digits or 1,000 digits. Nevertheless, you can compute a to the power of b mod c efficiently. So let me try to explain why that is. Let me give a small example, but these are those kind of things you should always think about when you're trying to develop, say, algorithms or numerical algorithms. How would I do this if I had to do it by hand? Because your computer's algorithm is just going to be like your by hand algorithm, only somewhat faster. OK, so let's say we want to compute 2,300 and whatever to the 32 mod 100. So a bad idea would be to do what I said before. Just be like, all right, first step, let's compute 2,337 to the 32. So that's 337 times itself, which is this, times itself, which is this, times itself, which is kind of going to be a drag. I mean, if there's like $1 million prize for doing this in one day, you would probably do it. But it would be a lot of suffering. OK, this is the final answer. But then you would say, aha, but mod 100, it's 81. So I got the answer. So that's a bad idea. But there's actually 2 ideas you can use to speed this up. So I think maybe you guys can figure out these ideas. Can somebody suggest one idea that will make your life a lot simpler? Yeah? Exactly, yeah. I mean, only look at the last 2 digits. Or just always work mod 100. I mean, if you know the final answer you want, it's just whatever it is mod 100, then you can just always be taking your numbers mod 100. And in fact, in that way, all your intermediate calculations will only be 2 digits long. Or maybe 3 digits if you have to square them. So that's one smart idea. Good thing we did it in this order. Somebody suggest another good idea? Yeah?
You can find a number such that 2337, that number is 1 mod.
Okay. Well, I'm not sure how that will. It's not so clear that that will help. I mean, first of all, how are you going to do that? But second of all, it's a question of. Actually, well, I mean, we're going to actually talk about this idea later, but it's not what I was going for here. You had your hand up before, yeah?
Yeah, since we're doing two-digit only, we don't really need to do this sequentially. We can just square them and square them and square them. Do a little knockout operation.
Yeah, actually, I mean, what you said doesn't have anything to do with whether or not we're only worrying about 2 digits or whether we're doing this smart idea. But it is what I was going for. You know, since you're raising something to the power of 32, actually, you don't have to do 32 multiplications. You can do like only 5 kind of multiplications. You can just square the number 5 times. And of course, you can put these two ideas together, actually, which I guess is what you were saying. But just looking at this idea, you know, if you do this number and you square it, you get to the power of 2. You square it again, you get to the power of 4. You square it again. You know, each time you have to do 5 squarings, which is like 5 multiplications. So that's a lot better than doing 32 of them. And of course, you can put these two ideas together. So you actually only compute these squared numbers mod 100, or keep their last 2 digits. Now, you might say, yeah, that was kind of lucky, though, that the exponent here was 32, which is a power of 2. You know, what if you're trying to figure out this number to the power of 34? You can still do something almost as smart, maybe even smarter, arguably. Yeah?
You can go up to the closest power of 2 and then just use the ones you've already calculated to get to the remaining. Like if you get to the power of 32, to just multiply it by the squared to get to the power of 34.
Yeah, exactly. As long as you've got up to this number to the power of 32, in the meantime, you also computed these other powers. And you can just multiply this one together with this one. And that'll give you the thing to the power of 34. What if you wanted to the power of 53? Yeah, it's what you're saying. Yeah. We can get this, I mean, without too much more work, given that we know this information, by just multiplying together the appropriate powers. Like, because 32 plus 16 plus 4 plus 1 is 53. So if we multiply this one, this one, this one, and this one, we get the thing to the power of 53. And how did I figure that out? This is just the binary representation of 53. It tells you like all the powers of 2 you need to add up to get to 53. So if you by squaring compute all of the numbers to the powers of 2, then you can just add, well, you can multiply up the ones you need based on the binary representation to get what you want. OK, so in general, to do this computation of a to the b mod c, where these are n-bit numbers, the first thing you do is just repeatedly square a n times, but you always take it mod c. OK, so this prevents the numbers from getting really long. Since you're always going mod c, you're always working with just n-bit numbers. And we can do multiplication or squaring also in poly n time. So this whole thing is poly n. And now you have a to the power of 1, 2, 4, 8, 16, et cetera. And you look into the binary expansion of b. And it tells you that b is like the sum of some powers of 2. And you multiply together those powers of a that you cooked up that were to the power of powers of 2 to get a to the b. Just like in this case, we can get like this thing to the 53 by taking the 32, 16, 4, and 1 and multiplying them together. Yeah?
So does that mean if I knew like 37 to the power of 53,
yeah,
that's the same as 2337 to the power of 53?
Yeah. Oh, well, mod 100.
Yeah.
Yeah, so this is something I'll mention. I think you know some things, hopefully, about modular arithmetic, but I'll remind you a little bit. If you take two numbers, let's say mod 100, and multiply them, it's the same as if you multiply them and then take them mod 100. Well, if you also mod 100 again at the end in the last step. So in particular, if you want to do 2337 squared mod 100, you can also do just 37 squared mod 100 and then take that mod 100. OK, yeah? Why is it a little bit more? Because the running time for multiplication is like a little bit more than n log n. It's like the fastest one is like n log n times 2 to the power of log star n or something. But it's basically n log n. And as I said, I don't want to get like too overly excited about the exact running times here. It's enough for us that it's a polynomial time. OK, let's move on to talk about another important numerical algorithm, which is that of computing the greatest common divisor of two numbers. It's probably something you're taught how to do in school as well. Maybe you weren't sure why. Well, today you'll learn why. Finally, it's going to come together. So again, let's say you have A and B, and you want to find their greatest common divisor, the GCD. Well, in grade school, they teach you this algorithm. First factor A and B, and then you take the minimum of all the prime exponents or something. But that's a bad idea, right? We already saw that factoring A and B is going to take you forever, potentially. But you can do it, again, kind of amazingly in polynomial time. And I'll explain to you the Euclid's algorithm for doing this. Actually, I think Professor Uda mentioned this even in the first lecture. And what's pretty cool about this is it's really like the first algorithm ever. I mean, it's like a really old algorithm. It's pretty cool. Also, it was not invented by Euclid. It was invented like maybe a couple hundred years before. Euclid just like summarized a lot of known mathematical knowledge in his books. But it's called Euclid's algorithm anyway. OK, so let me try to figure out how to do this GCD instead of just immediately telling you the algorithm. Let me make some observations. Suppose we got these big numbers A and B, and suppose G is some divisor of A and B. Then I claim it also divides evenly into A minus B. Right, because 6 divides 6, 112, so it also divides their difference, which is 588. Just if this is a multiple of 6, this is a multiple of 6, then of course this is also a multiple of 6. OK, so that's good. What would be really cool if it wasn't just that whenever you had a divisor of A and B, it also divided A minus B. What would be really cool is if the GCD of A and B was always the GCD of A minus B and B. And the reason is that would be kind of cool is you could sort of use that to reduce the computation of the GCD of A and B to like a smaller GCD problem. Because A minus B is smaller. So you could say, well, it's the same as the smaller problem. And then I'll try to maybe recursively solve that smaller problem and sort of keep making progress. But is this really true? Yeah, it is true. Because conversely, if you have some divisor G that divides into A minus B and B, then it also divides into A. Like if this is a multiple of B, if this is a multiple of G and this is a multiple of G, then their sum is also a multiple of G. So in fact, every number that divides A minus B and B also divides A, and conversely. So the largest common divisor has to be the same. I mean, the set of numbers that divide A and B is exactly the same as the set of numbers that divide A minus B and B. So this is true, and we can use it to do this GCD computation in a way that sort of makes the numbers smaller and smaller until we get the answer. OK. So let's do an example. Sort of not the full Euclid's algorithm. It's kind of a warm-up. And this is definitely also, again, historically known before Euclid's algorithm was known. It's called subtractive GCD algorithm. Let's say I want to compute the GCD of these tiny numbers, 42 and 30. Well, I use this idea that I can do, it's the same as the GCD of 30 and 42 minus 30, which is 12. So now I've reduced the computation to a smaller one. OK, and then that's the same as the GCD of 18 and 12, because I can just subtract 12 from 30. That's the GCD of 12 and 6. And that's the same as the GCD of 6 and 6. And it's the same as the GCD of 6 and 0. And now I'll stop. Because if you have the GCD of like a number and 0, it's definitely that number, right? I mean, the GCD of the largest divisor of A is certainly A. And that will also always divide evenly into 0. So we've got our answer. OK, so we got the answer. Any questions about that? OK, so that's good. This is an algorithm for computing the GCD. It works pretty good if the numbers are small, but let's try another example. Let's do the GCD of 6,004 and 6. Actually, these numbers are not so big either. So we're all right. It's the GCD of, I'll subtract 6 and get 5998 and 6. And I'll subtract 6 again and get the GCD of 59982 and 6. 598 and 6 and 6. This is going to go on for a little while. But I think you guys are smart. We could probably skip a lot of steps, right? Like, in the end, we're going to get down to, at what point will we get down to something where things will change? What will go in here? 4, yeah, right? Because we'll keep subtracting 6 from this number like many, 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 many times. After 1,000 times, we'll get down to 4 and 6. OK, and then we're like almost done, right? Then we'll say it's the same as 4 and 2, and 2 and 2, and 2 and 0, and the answer is 2. But in general, like, if you wanted to skip all these intermediate subtractions, if you have GCD of A and B, and A is like way, way bigger than B, what will you get down to here? Yeah, A mod B. You'll get down to the remainder of A when divided by B, because you'll just keep taking out copies of B until you're left with something smaller than B. OK? So what this is telling us is in this GCD algorithm, instead of just subtracting the smaller number from the larger number, we can do the larger number mod the smaller number. And this is still a correct algorithm, right? I mean, we're just taking the old algorithm and just speeding it up by like doing these intermediate steps all in one shot. But it actually speeds up the algorithm a lot, which is good. Any question about this? So here's Euclid's GCD algorithm. I mean, I've told it to you now. For fun, I just wrote it recursively, so it'll be like 2 lines long. But it's just a very, very simple loop. Maybe it would have been 3 lines if I had used a loop. If you're computing the GCD of A and B, just assume that A is bigger than B. If not, you can switch them. If B is 0, then we're done. The answer of GCD of A and 0 is A. Otherwise, we'll do GCD of B and A mod B. OK, and A mod B is legal because B is not 0. OK, so here's an example. I'll do it again with small numbers. GCD of 118. First, we do 100 mod 18 is 10, because 5 times 18 is 90. OK, and then GCD of 18 and 10, we do 18 mod 10, which is 8. So we switch to GCD of 10 and 8. 10 mod 8 is 2. So we go to GCD of 8 and 2. 8 mod 2 is 0. So we get down to GCD of 2 and 0. OK, and then we say the answer is 2, which is correct. OK, so we're going to study this algorithm a little bit more. Let me just say like a summary. If I'm talking about this algorithm later, like this is basically the summary. If you're starting from 118, this number mod this number is 10. This number mod this number is 8. This number mod this number is 2. And you go down until, I don't know, you get to 0 or until this number divides into this number. OK, so we have a correct algorithm to compute the GCD. Now, as usual, we care about what is its running time. And again, imagine these are really huge numbers with like hundreds and hundreds of digits. Well, let's look at this. At every step, we do one number mod another number. And this is polynomial time, right? We talked about the algorithm for division. It's polynomial time. So computing the mod is polynomial time. So basically, we only need to show that like we do a polynomial number of these big steps. Or, you know, the number of lines in this execution trace is polynomial in the number of digits of the numbers. OK, so let's imagine what happens. I mean, the general idea, if you play with around this for the second, is you see that as you keep doing like mod of this, mod of this, mod of this, the numbers get a lot smaller quite fast. They kind of get like exponentially smaller as you go along, which is exactly what we need. So let me prove that to you. So let's say we're going through the algorithm, and at some point we've got GCD of A and B, and the next thing we do is compute A mod B. And I kind of want to tell you that like in doing that, like the numbers have gotten noticeably smaller. And in fact, what I'll specifically claim is that when you go from A to A mod B, that number decreases by a factor of half or more. that this number is at most half of this number. Okay, and that's very straightforward to check. There's two cases. One is if A is like really big compared to B, or even if A is just bigger than 2 times B. If A is bigger than 2 times B, well, I don't know what A mod B is, but it's definitely less than B. So in this case, this number is less than B, but this one is bigger than 2 times B. So indeed, you've gone down by a factor of at least a half. The other case is when A, it's bigger than B, but not too much bigger. Let's say A is at most 2B. In particular, in that case, A is somewhere between B and 2B. So then you compute A mod B. Well, A is between B and 2B, so A mod B is really just subtracting B one time from A. So you got, and going from here to here, in this case, you subtracted off B. But B is bigger than half of A. That's exactly the case we're in. So the amount you subtracted off was at least half of the initial amount. Okay, so it's just like a very simple little case to check. I mean, if you play around with this, you'll see that indeed the numbers go down quite fast. So what does that mean? When we go from A and B, in the next iteration, we're going to be like, this will be our pair of numbers. What I want to say, this is like kind of a cute way to figure things out. This product, this number times this number, is at most half of this number times this number. Right? Because this product, they both contain the factor of B, so you can ignore that. And we just showed that this one is at most half of this one. So exactly what this is saying is that, as you're going along in this GCD computation, you have 2 numbers, and then you mod 1, and you get 2 new numbers, you get 2 new numbers, 2 new numbers. The product of those 2 numbers always goes down by a factor of half or better. Okay, and that's really great. That will let us finish the analysis. So the total number of steps, well, basically, you have something that's going down by half each time. The total number of steps is going to be log of that thing. So the total number of steps is at most log of AB, just log A plus log B, which is the length of A plus the length of B. So the overall number of, let's say, recursive calls or iterations of this loop is basically equal to the total number of digits in the input, which is good. Right, so if these are n-bit numbers, the total number of overall steps is order n. Inside, you have to compute the mod, which, the grade school does it in n² time. You can do a little bit faster. Anyway, the whole algorithm is polynomial in n. Any questions about this? Okay, great. I want to mention just one slide about some interesting facts about GCD problem, because it's really one of the most interesting problems in computer science, I think. And I'm curious about its intrinsic complexity. So Euclid's algorithm computes the GCD in polynomial time. If you're very clever, it's something like quadratic time. Again, if you type 2 1,000-digit numbers into Maple and ask it to compute the GCD, it will do it very fast, and it will not do this, because quadratic time is actually a little bit slow if the numbers have tens of thousands of digits. There are faster algorithms that are more sophisticated. You might be surprised to think that there's something even better than Euclid's algorithm, but there is. And almost linear time. But that's also sophisticated to analyze. And there's also a very truly major open problem, like a really tremendous open problem associated to computing the GCD, which is we've seen that GCD you can compute efficiently. The question is, can you compute it efficiently in parallel? It's an efficient parallel algorithm for it. And if you look at Euclid's algorithm, it seems kind of tough because, not like we're really going to define parallelism formally in this class, but it seems pretty sequential. Like you got to go 100, 18, 10, 8, 2. How could you sort of skip to the middle steps, And this is a huge open problem. And if you want to a very concrete, technically correct statement, just for kicks, you can phrase it this way. This is one way to phrase it. Let's try to think about solving GCD by circuits that take as 2 inputs that are n-bit numbers and output the GCD. They have n output bits. Is there a circuit family that does it that has polynomial number of gates, which we always want, but also depth, which is logarithmic, polylogarithmic? That's a formal version of this open problem. So this is a great mystery about GCD. OK, I'm going to spend 5 more minutes on the GCD, partly because it's such an awesome problem, but also to illustrate a little bonus that comes out of Euclid's algorithm, which you may not have noticed. OK, I invented this weird definition for the purposes of this class, which, by the way, it's not a real term, so you cannot use it yourself, not even on the homework, but I get to use it in this lecture. So let's say you have 3 numbers C, A, and B. I'll say that C is a mix of A and B, and this extra I stands for integer. So it's like an integer mix, an integer linear combination of them. OK, so if C is expressible as some integer times A plus some integer times B. Okay, it's like a linear combination of A and B, but the factors are integers. OK, so as an example, 2 is a mix of 14 and 10, because 2 is negative 2 times 14 plus 3 times 10. That's 30 minus 28. Okay, and I do this example to emphasize that these K and L can be negative. Okay, so 2 is a mix of 14 and 10. And actually, once you know this, you know that any multiple of 2 is a mix of 14 and 10, because if you wanted to get like, I don't know, 6 as a mix, you can just multiply this by 3. All right, and you have like minus 6 times 14 plus 9 times 10. OK, let's do a non-example. 7 is not a mix of 55 and 40. That's easy to prove, right? Because if you do a mix of 55 and 40, it doesn't matter what coefficients you use, you're going to get something divisible by 5. Right? And so you can't get 7. Actually, let's take a look at this statement again a little bit more carefully. In general, right, if you have 2 numbers A and B, then any mix of them, and they're both divisible by some number f, then any mix of them will also be divisible by f, because it doesn't matter how you combine them, right? The thing is going to be divisible by f. So, in particular, even the greatest common divisor of A and B will have to appear in any mix of A and B. So if you have a mix of A and B, it has to be a multiple of the greatest common divisor. So if you're wondering, I mean, now it's maybe natural to wonder, well, conversely, is it true that the greatest common divisor is always a mix of the 2 numbers? If this is true, then this would be an if and only if, right? Because the GCD is always a mix. We saw before that once you get some number as a mix, you can get any multiple of that number also as a mix. So this is going to interest us. Is it true that the GCD has to divide into any mix, but is it true that you can always get the GCD as a mix? And the answer is yes. And you might wonder why we care. Well, we're going to care later in this lecture, but the answer is yes, and it's a bonus of actually Euclid's GCD algorithm. If you run Euclid's GCD algorithm, it's almost like a proof that the final answer, the GCD, is a mix of the 2 initial numbers. And let me show you why. I'll just sketch it in an example. So this is an example of GCD running on 118. The final answer is 2. So what I'm telling you is that 2 is somehow a mix. It's like an integer linear combination of 118. And somehow you get that mix by like looking at these intermediate steps. So here's the summary of getting GCD of 118 equals 2. We went from 100 to 8 and 18 to 10 to 8 to 2, always doing mod of the previous 2 numbers. And let me just make a couple of quick observations. If A mod B is R, then R, the remainder, is always a mix of the 2 numbers A and B. Because by definition, right, R is like A minus some multiple of B. And this is the mix. R is like 1 copy of A and minus Q copies of B. OK? And another thing that's very easy for you to check, it's just like it sounds. Like if R is a mix of A and B, but B itself is a mix of A and C, then you would guess, and it's trivial to check, that R is a mix of A and C, or just R is a mix of A and C, just as you would guess from the name. Now let's just take these 2 facts and sort of apply them to this chain going right to left. So at the end of this chain, we have that 2 is 10 mod 8. So by fact 1, we know 2 is a mix of 10 and 8. OK. Now, but what about 8? See, 8 was 18 mod 10. So we also know by fact 1 that 8 is a mix of 18 and 10. But now 2 is a mix of 10 and 8. And 8 itself is a mix of 18 and 10. So 2 is a mix of 18 and 10 by fact 2. It's OK? And now we'll keep going, in a sense, to get rid of 10. Because 10, being 100 mod 18, is a mix of 118 by fact 1. So 2 is a mix of 18 and 10. 10 is a mix of 118. So fact 2 tells us that 2 is a mix of 118. And actually, this is a very short example. So now we're actually done. We've sort of shown that 2 was a mix of the initial two numbers, 118. But if this were a longer computation, then you just keep going back in the chain, applying fact 1, fact 2, fact 1, fact 2. And writing the final answer, 2, as a mix of these pairs of numbers as you go back. OK, so I won't do a long proof or anything. But the summary is that if you have A and B, then their GCD G is always a mix of them. And you can get it by running Euclid's algorithm on A and B and getting down to G, and then kind of doing all these fact 1, fact 2 observations all the way back to the beginning. And so in particular, not only is it a mix, you can actually find what the mix is, like what K you need and what L you need from Euclid's algorithm if you just do a little bit of bookkeeping as you go along. OK, so to summarize this bonus of Euclid's algorithm, if you have A and B, their GCD is a mix of A and B, and you can actually find the coefficients that give you that mix in polynomial time. OK, any questions? OK, so we're 2/3 of the way through the lecture, and let me summarize what we've seen. Actually, that section was a nice chunk. It was just a story of efficient algorithms and lack of efficient algorithms for a lot of basic arithmetic problems. So lots of things we can do efficiently, including, interestingly, primality testing, GCD, modular exponentiation, and some things we don't think are efficient, like factoring, and some things we definitely know are not efficient, like factorial or just non-modular exponentiation. OK, so the last thing I would like to talk about in the last third of the class is a little bit of actual number theory. I mean, this is a bit algorithm-centric. We're going to talk about number theory for a little bit in preparation for doing cryptography. But at the very end, we'll see a little bit of connection to the primality testing problem. OK, so I hope you've all seen some modular arithmetic. I'll give you a little refresher on it. So sometimes in arithmetic, we have a number m, and we decide to work modulo m. OK, so like on a clock, the hours are kind of mod 12. On computer hardware, the actual machine instructions are doing computations mod 2 to the 32 or 2 to the 64. And what does that really mean? Well, every integer, it has a remainder mod m. And we kind of think of that number as being equivalent to its remainder mod m. And actually, we say that A and B integers are equivalent mod m if they have the same remainder mod m. This is sometimes written A equals B mod m, which you can write, feel free to write, but I prefer to write it like this. A is equivalent to B, and this subscript means modulo m. OK, so once you fix m, it divides the numbers up into equivalence classes, the ones that have the same remainder as mod m. And every number is equivalent. I mean, the sort of the standard representations of these equivalence classes are just the good old remainders 0 through m minus 1. OK, so let's review a little bit about doing addition mod m. And addition and modulo m work together in a very gentlemanly fashion. Like everything that you want to be true is true, and there's no worries. So in particular, you could say that addition mod m commute. Like if you have A is equivalent to B mod m and A prime is equivalent to B prime mod m, then A plus A prime is equivalent to B plus B prime. OK, so if you're working mod m, you could just do pluses as you always do, and everything works fine. So in fact, one way you can say this, if you're getting a little bit more sophisticated, instead of just writing mod m after every single line, sometimes we define a new number system, the notation for which is z sub m. It's like the integers mod m. And this is like a number system where there's m elements, 0, 1, 2, 3, up to m minus 1. And it has an operation on it, plus. Okay, but like you define, like this plus is like always plus mod m. So for example, z5 means the set of numbers 0, 1, 2, 3, 4, like the remainders mod 5. And addition, when you're talking about of numbers in z5, has this table, right? Like 2 plus 3 is, 2 plus 1 is 3. That's like normal, mod 5. But also like 2 plus 4 is 6, but you do mod 5. So it's 1 mod 5. Okay, so if you're working in z5 or you're working mod 5, this is how addition works. 4 plus 4 is 3. Because it's also 8. Okay, if you haven't seen the notation z5 before, I'm telling it to you now, but I hope you at least have seen this concept before. And just a quick reminder, in this world, 0 has a very special property. It's the thing that, if you do plus to it, it doesn't change the number. So 0 plus a is the same as a plus a, it's a. Okay, so that's about addition, mod m. And you might say, what about subtraction? That's my other next favorite operation. And you can do subtraction mod m, of course. You can do all your arithmetic mod m. But to define it, actually, the way we like to define it is, instead of explicitly saying, how do I subtract two numbers in Zm, I'm just going to define what it means to take the negation of a number in Zm. And then if you know what negative b means, then a minus b can just mean a plus minus b, okay, which you can figure out by looking at that table or, well, just doing the computation. So in other words, we're going to define subtraction in terms of defining the negative of a number. And one way you can define it is, the negative of the number, just do the regular negative of it over the integers and take it again mod m. But let's do it in a slightly different way. The way we can define negative b is just to say negative b is whatever number you need to add to b to get 0. I mean, in some ways, that's the definition of negative b, right? But we can do it by looking at this table, right? So in z5, if I want to know what is negative 2, well, what is it? Yes, 3, because it's the number you need to add to get to 0. Okay? Or negative 4, you look until you find the 0, and it's negative 4 is 1. Okay, and negative 0 is 0. It's the same thing. You add 0 to get 0. Okay, so that's great. Everything is fine. And this b, negative b always exists and is unique because each row is going to have exactly 1 0 in it. I mean, each row is just like a cyclic permutation of the numbers, 0 through m minus 1. Okay, so far so good, I hope. Any questions? Just telling you things you kind of already know in a slightly different way. Okay, well, what do you learn in school? There's plus, and there's subtraction, and then the next one is multiplication. So let's talk about multiplication, mod m. And multiplication also plays a perfectly nice mod m. If you multiply two numbers and then do mod m, it's the same as doing mod m and multiplying them and doing mod m again. We mentioned this earlier. So you can define all your multiplication as the same way when you're working mod m. And again, we can just think of it as a table. Like if we're going mod 5, there's like 5 numbers. The remainder is 0 through 4. And here's how you do multiplication, right? Like for example, 3 times 3 is actually 9, which is 4 mod 5. So when you're working mod 5, 3 times 3 is 4. Or 4 times 3, it's really 12, so that's 2 mod 5. And when you're doing multiplication, 1 is the number with the special property. The number that if you multiply 1 against anything, you get the number back. Okay, so things are all looking well and good. So we're like, let's go to the last one, division, right? Now division, there's a bit of a problem with division when you're doing integers, right? You cannot always divide an integer by an integer and get an integer, but let's see what happens here. Well, we could just say look, it's going to be similar to subtraction, right? If I want to define a divided by b, let me just try to define the reciprocal of b inverse. Okay, and then if I do that, then I can just get a divided by b. I'll just say that's a times the reciprocal of b. OK, and so given b, you would just say, hey, maybe I'll define b inverse to be that number, which in the table, which if you multiply it by b, you get 1. That's what it's supposed to be, right? But there's a bit of a problem with this. So let's take a look at what happens if we try to do this. So let's look at the reciprocals of numbers mod 5. OK, so 1's reciprocal should be what? 1. Yeah, you look in this thing, and you're like, aha, if I multiply it by 1, I get 1. Perfect. 2's reciprocal is 3, because you're like, all right, there it is. There's the 1. 2 inverse is 3. And that's really because, 2 times 3 is 6, which is the same as 1 mod 5. And 3's reciprocal is 2. And 4's reciprocal is 1. Sorry, it's 4. Thank you. OK, well, 0's reciprocal is undefined, because there is no 1 in this row. But that's OK, right? We're used to not being able to divide by 0. So we're like, yeah, of course. You can't divide by 0, so it's fine that there's no 0 inverse. So everything looks more or less cool so far. But let's go to mod 6, and we'll see there's a bit of an issue. You can see it already, probably. We're like, OK, the inverse of 1 is going to be 1. The inverse of 2 is, now we're stuck. It's undefined. There is no number you can multiply by 2 to get 1. There is no inverse to 2. That's it. Sorry. There's no inverse to 2. Just like you can't divide by 0, you can't divide by 2, mod 6. And you can't divide by 3, and you can't divide by 4, although you can divide by 5. If you do 5 times 5, that's 25, which is 1 mod 6. And 0, of course, is still undefined. That was interesting. We only have 2 numbers that have inverses mod 6. Well, let's keep checking to see what happens. If we go mod 7, here actually everything looks good. You have a 1 in every row, except for the 0 row. You're never going to be able to divide by 0. But every other number you can divide by. I mean, every other number has some inverse. So that's good. Maybe 6 was just really bad. Well, we can look at 8. You can see it's sort of good, sort of bad, right? I mean, if you look carefully, 1, 3, 5, and 7 have an inverse, have a reciprocal. 0, 2, 4, and 8 don't have a reciprocal. Well, it's a fact of life, I guess, that if you're working mod some number, sometimes you can do reciprocals of other numbers, sometimes you can't. Of course, it makes you ask the question, right? Like, when is a number going to have a reciprocal mod m? When is b going to have a reciprocal mod m? Or when are we going to find a 1 in this row of the multiplication table, the bth row of the multiplication table mod m? Well, it has a straightforward answer, actually. I mean, b has a reciprocal mod m if there's some number k such that k times b is congruent to 1 mod m. OK, let's just expand this definition. If there exists a k and a number q such that kb is 1 more than a multiple of m, that's what it literally means. And let me just rearrange this equation. It's if there exists k and q such that 1 is k times b plus minus q times m. So, I mean, q and minus q, it doesn't really matter. It happens if you can find 2 integers, you multiply by 1 by b, 1 by m, you add them up and get 1. That's the same as saying that 1 is a mix of b and m. Okay, these are all if and only ifs, right? So that's it. B has a reciprocal of mod m if 1 is a mix of b and m. And actually, we have another way we can say what that means. Yeah, it's if the GCD of b and m is 1. OK, so this is what you should definitely remember. If you're working mod m, then the number b has a reciprocal if and only if its GCD with m is 1. Sometimes the math people say b and m are coprime. And that's good, right? I mean, for example, we know how to do GCDs in principle and in practice. So we can kind of tell which numbers are going to have reciprocals and which ones won't. And let's just check this. Mod 5, we saw that 1, 2, 3, and 4 had reciprocals. And indeed, GCD of 5 in all these numbers is 1. And GCD of 5 and 0 is not 1. Mod 6, only 1 and 5 had reciprocals. That's because 2, 3, and 4 have a non-trivial common factor with 6. 7, all the numbers except for 0 have GCD 1. With 8, all the even numbers have even GCD, and otherwise the GCD is 1, etc. And one nice thing to note is that if you're going mod a prime number, the GCD of a prime with everything smaller than it, other than 0, is 1, right? So mod a prime, you're very happy. All the non-zero numbers have a reciprocal. You can never hope that 0 has a reciprocal, but otherwise, all the numbers have an inverse. Mod a prime. So it turns out we're going to be very interested in, given a number m, which might not be prime or it might be prime, we're going to be very interested in all the numbers that have inverses. Or equivalently, all the numbers that have GCD 1 with our m. And there's some notation for this. It's Zm star. I mean, the star stands for multiplication. So we came to here by thinking about multiplication. Okay, so this is important notation. There's this weird notation that I guess you'll have to learn. The cardinality of this set, the number of numbers between 0 and m with GCD 1, is written phi of m. I never remember how to pronounce this. Phi of m. Which is annoying. It's invented by this guy, Euler. So here's an important fact that I'll illustrate on the next slide. If you just collect up all the numbers that have an inverse together and call them Zm star, this thing is closed under multiplication, which means if you take two of these numbers that have inverses and you multiply them together, mod m, that thing also has an inverse. Can somebody say why that is? Yeah?
You just multiply the two inverses together and get the new inverse for AB.
Yep. I mean, A times B has a reciprocal because there it is. It's B inverse times A inverse. And like by assumption, these things exist. If A and B have inverses, B inverse, A inverse exists. And if you multiply this by this, you get 1. So that proves that this also has a reciprocal. Okay, so that's kind of cool. It means if you collect together all these numbers that have GCD 1 or have reciprocals, they make like a nice new little number system where you can multiply numbers together. Let me give an illustration. If you want to make Z5, well, you start with the multiplication table, but now we get rid of 0. It doesn't have an inverse. Okay, so in Z5, there are 4 numbers, 1, 2, 3, 4. The remainder is mod 5, but only a specific subset of them. And you can do multiplication on them, and it always stays within the set 1, 2, 3, and 4. And phi of 5 is 4, because there's 4 numbers here. In general, if p is prime, then phi of p is p minus 1. Yeah, remember, it's the number of things in this table is all of the numbers mod of prime have GCD 1 with it except for 0. Let's do another more interesting example. If we look at Z8 star, we start with the multiplication table, but we get rid of all the ones that don't have inverses, that have a 0 in their row or column. This is annoying to look at, so I'll draw it like this. So just the ones that are left are 1, 3, 5, and 7. And it's a nice fact that if you multiply, 5 times 3, it's 15, which is 7 mod 8. Like this multiplication stays within this set.
This was a homework problem, wasn't it?
This was a homework problem?
Earlier homeworks, there was a problem with this.
Was it a homework problem? I don't remember. This whole course has been a blur. All right, great. Which one?
It was like we had to, you gave us the rules of the group, but you didn't tell us it was a group.
Oh, a little bit, yeah. The one with it's not too similar to this, but yeah, you had to make these, you had to think about these tables of number systems or a group where multiplication was maybe a little bit different from normal. Yeah, these objects are actually called groups, but we won't study that in this class. Here's a bigger example. C15. I already did the step of deleting all the rows. I took the 15 by 15 thing, crossed out all the numbers that had a non-trivial divisor with 15. So what's left is 1, 2, 3 you had to get rid of, 4, 5, and 6 you had to get rid of, 9 and 10 also have common factors, so does 12. So you're left with 8 numbers. And this is the table. Okay, you can check. And as you see, they all stay in the set when you do multiplication. So phi of 15 is 8. And here's a little exercise for you. It's pretty easy, but you should try it, especially in preparation for the next lecture. If p and q are distinct primes, then phi of pq is p minus 1 times q minus 1. This is like saying if you look at all the numbers up to p times q, the number that have GCD 1 with pq is p minus 1 times q minus 1. You can see it worked out here, right? 15 is 3 times 5. So this would be 2 times 4, which is 8. OK, try it. It's not too hard. Actually, there's another interesting property of this table. Can anybody guess what I'm thinking? I mean, it's hard to guess, but another. It is definitely symmetric if you like fold it this way, right? Because that's a good point. Multiplication commutes, right? So I mean, anything you see in the 8 times 4, 2 is the same as 4 times 8. Any other properties? Yeah. Yeah, each row has the same numbers. It's not just that like when you multiply 4 by anything, you stay within this set. Actually, you get like every number in each row. Like each row is a permutation of the basic numbers. Right? Like every number in ZM star appears exactly once in each row. Yeah?
Row 7 has 2 7s and no 8.
Oh, very good. That's a typo. So what should it be? Which one is wrong? 14 times 7? Should be what?
Guessing 8.
Yeah, it should be symmetric, right? Let's see. This one?
Yeah.
Should be an 8? All right. Thank you. Oh, it's going to go back to the beginning. Oh, that's going to screw everything up for Nathan. Sorry, Nathan. This was a disaster. When you hit F5 in PowerPoint, like it goes to the start, which is very annoying. Normally I have like this keystroke remapper that opens up on the current slide, but I forgot to run it. Okay, almost there. Well, I need to kill a few minutes anyway. Okay, why did you have to bring that up here? No, I'm kidding. Thank you. Is it still not wrong? Oh, I gotta fix that. Okay. It was still what?
You fixed one of them.
All right. Well, I'm gonna fix it later. Okay, good. This one is okay, right?
Yeah.
Okay, good. Phew. Yeah. So why is that? You probably saw as I was looking through the slides. Why is that? Why do you get all the numbers exactly once here? To say that's actually a permutation is just to say that no number appears more than once. In other words, all the entries have to be distinct. And that's because, I mean, let's say you're looking at the A row. You're doing A times all these numbers up here. If you ever had A times B equals A times B prime, well, by definition, A has an inverse, A inverse. You could multiply this equation by A inverse and get that B equals B prime. So that's like saying any two columns in a specific row have to have distinct answers. Okay. Now let me show you a little trick. It's a nice fact. Now that we know this, that each row contains like a copy of all the basic elements of ZM star just in a different order, this is just like an interesting trick. Let's pick your favorite row, like maybe row, oh, our favorite row is now row 8. Or was it row 7? Row 7, okay, our favorite row is row 7. So let's take row 7 and multiply all of its entries together. Just multiply all of them. So on one hand, by definition, what are the entries in row 7? This is 7 times 1, 7 times 2, 7 times 3, 7 times 4, up to 7 times 14. 7 times 14 is 96. Okay, yeah. No, sorry. 98. Good. By definition, it's this. Right? That's just what it is. But on the other hand, we also know that whatever these entries are in the 7th row, it's the same as all the basic numbers, right? So it's just 1 times 2 times 4 times 7. I mean, just in the first row, for example. So these two numbers are equal. But like, you see there's like a lot of common factors that you can cancel out. I mean, one of each of the numbers. And you really can cancel them out, right? Because each of these numbers, by definition, has an inverse, mod 15. So if you multiply this equation by the inverse of this, you're just left with 8 copies of 8. 8. So once you divide through, you get 8 to the 8 equals 1, which is a neat trick. Okay? And that actually worked for any number here. So for any number here, if you multiply by itself 8 times, you'll eventually always get to 1. Any question about that trick? And I didn't really use any properties of like 15 here. So what would this 8 be in general? If you're going mod m? Yeah, it would be phi of m, because I mean, when you do this, you multiply everything in the row, you get like a copy of a for each element in zm star. And by definition, there are phi of m elements in zm star. Okay, so what we just showed is this. It's called Euler's theorem. If you have any m and any a, well, a has to be in z mod zm star, so it has to have GCD 1 with m. For any m and any such a to the power of phi of m, whatever that is, it's always equivalent to 1 mod m. Okay, this is a nice fact, and I think as you'll see next time, it helps you with understanding exponentiation mod number m. It has like a corollary which is quite simple and nice. It's called Fermat's little theorem. When m is prime, you see that phi of m is m minus 1. We saw that before. So just when m is prime, you get that if p is prime and a just has to not be divisible by p, a to the p minus 1 is congruent to 1 mod p. Okay, that's a good trick that gets used a lot in elementary number theory. A to the p minus 1 equals 1 mod p for prime p. Now actually, if you look at that for a second, it kind of looks like somewhat like a characterization of a prime. Actually, it only goes one way. If p is prime, then this is true. But it might suggest to you some kind of potential primality test. For example, let's say you're given some m and you're trying to tell if it's prime or not. I'm not saying this is going to work. There's one thing you could try is just pick a few random a's between 1 and m minus 1. And for each one, compute a to the m minus 1 mod m. Okay, and we can do this efficiently, right? Because this is exactly modular exponentiation. Something to something else, mod a third thing. You can do that efficiently. And if you ever happen to get 1, you know for sure m is not prime. By Fermat's little theorem, it's composite. So if you ever get 1, not 1, you can just say m is composite, and you're right. And maybe otherwise you might say, well, perhaps m is prime. You know, especially if you try this for a lot of a's. You know, you might have this rough intuition that, like, look, if you do this weird computation, m is a prime. You know, there's a lot of numbers between 1 and m. You know, if it's like a quator vigintillion, that's a lot of possibilities. I mean, if you miraculously get 1, you might kind of think, hey, man, maybe m is prime. Now, it's actually a good idea, but unfortunately it doesn't work. Because very annoyingly and interestingly, there are these few rare numbers m, which are called Carmichael numbers, which have the annoying property that they like satisfy Fermat's little theorem somehow. Like a to the m minus 1 minus mod m is always 1 for every a. So if you run this algorithm on a Carmichael number, it's going to always say prime, even though they're also composite numbers, I should say, even though it's not prime. So that's a shame. It's a good idea, though. And in fact, this is the basis of the Miller-Rabin randomized primality test I told you about. It does this, and it does a few more extra number theoretic steps that fix the Carmichael number problem. So I mean, it's a little too complicated to explain. It would maybe take, an hour. So we're not going to do it. But this is the idea behind it. And let me just add one more thing. Sometimes in life, you don't want to just check primality. You want to generate a random prime number, especially if you're doing cryptography. This is a very common step. Generate a random prime number. And how do you do it? You pick a random number, check if it's prime. Pick a random number, check if it's prime. And you keep going until you find one that you think is prime. But these Carmichael numbers you can prove are extremely rare. So when you pick a random number, you can prove that it's very, very, very unlikely to be a Carmichael number. And so actually, you can also prove that this test works with high probability if m itself is random. So actually, this simple thing works very well if you want to get a random prime number. And in fact, you'll get the right answer with high probability, even if you just test A being like 2 and 3. So this is actually a very efficient algorithm for generating a random prime number, more or less, that works with high probability. OK, see you next time.